All right, this is your Professor Schwitkus talking about astronomy, and in this section, we're going to be talking about looking up in the sky and how would you go about describing where you're actually looking. So I start off with this picture. As you know, I'm a wannabe mountaineer. This was a morning or evening picture taken in the northern hemisphere, relatively close to Los Angeles, maybe depending upon your relative nature of distance. So I would start this off and ask people in the class, what is it that we're looking at? And am I looking west or east? What is this object here? And most people would say the moon. And what is this object here? And the questions would range from, is it night, is it sunset or sunrise? And more than that, the question is really, how do you know such things? And that is the primary discussion topic for this week. The sky, looking at the sky for the first time in detail, noticing the motions of the sky, the seasons, the phases of the moon and of the planets, and primarily to get us back into touch with those things that we have lost. What are the things that we have lost? Well, undoubtedly, most of you, like myself, particularly at your age, I had never seen the Milky Way. And I have only seen it a few times, and I've become more sensitized to it. I saw it for the first time maybe 3-4 years ago in Yosemite. So, that being said, we are disconnected from nature, from the world around us, and I hope with your help that you will devoid yourself of that notion. You will become more connected with nature. So, what is it that we're looking at here? Well, I think most of you would say that this is the moon because it has a crescent shape to it. And maybe some of you would be clever enough to say that this is Venus. Now, the question now arises as to where is the sun? And since I've given you a hint that this is the northern hemisphere, and that we are close to Los Angeles, then what is this here? And I'm sort of giving it away with some of the nature of the stuff here. But you don't need to have those hints. The moon is lit up because of the sun. And the sun, therefore, has to be pointing in this direction. The moon, or rather Venus, is also in this region where the planets move, and the moon is pointing at where the sun is, and the sun will move from this direction to where the moon is currently seen. So the sun is going to go in this direction. Now, if you look at the sunrise and the sunset, if you look at as you know, the sun rises in the east and sets in the west, but it will move at an angle with respect to the horizon, which is this horizontal line separating the earth from the sky. So in the east, when the sun rises, it makes an acute angle like this. It goes towards the south and rises. And in the west, it's going to behave in the opposite direction. So this is a sunrise picture. And this body of water turns out to be the Salton Sea. And I'm headed towards one of the hardest peaks to do in Southern California, called Big Rabbit. So how do we identify that light in the sky? Well, we've seen this chart before. It has to, and in particular, the way I want to use it this time is I want you to think about the lights that you see in the sky and where they are relative to your position in the sky. So when it comes to stars, there are only three things that we can measure directly from them. Everything is dependent upon these three measurements we can take. We can measure where they are in the sky, and primarily that's what we're going to be talking about in this lecture. We can determine if some stars are brighter than others. And if you look carefully, you can see that these stars are of differing colors. In particular, you can notice the red and the blue stars. And in particular, if you have a green laser, then you can really see the contrast between the colors. There are about 5,000 stars visible to the naked eye. You can see those in the desert or in the mountains. Here in Los Angeles, depending upon where you are, you can see about 500. And if you're underneath a street lamp, maybe one or two. So how do we go about telling somebody to look in the night sky and pointing out a particular object like a meteor or something and you want to share it? You can't really say, oh, it's that one over there. And in particular, if you use modern instruments, you have to be a little bit more careful about where you're actually pointing. So we're going to use this idea of a celestial sphere. Celestial spheres are basically a set of concentric balls. We have the Earth in the center here, and then outside there is a clear sphere of which we paint on there these representations of stars. If this is supposed to be the moon, it's sort of in the wrong place. But the idea here is this is how we go about describing what the stars look like. We'll see if this guy plays. So depending upon where we are in the sky, then the stars move around relative to us, right? I mean, the sky doesn't move. So if we put some stars up here, then, as you know, the Earth rotates and the stars stay put. But this is what it appears to us. It appears that the Earth does not move and that the whole sky moves around for us. This is also a nice way to introduce the idea of horizon and zenith and this type of motion. All right, so the celestial sphere is a way to describe the sky about us. And we can either cause the Earth to rotate or we can cause the sky to rotate. Either one will work as far as describing what we see in the night sky. And the reason that we can get away with it is during the course of the centuries, these stars do not move. And sometimes you might hear the idea of the fixed stars. So the stars rise and set, just like the sun. And some of them are called circumpolar stars. And this is Polaris here. It's very close to meeting up with the axis that the Earth is pointing at as it rotates, and so stars seem to rotate about this particular point. The circumpolar stars, as it says here, never rise or set, and here this particular star will rise, right? It rises up from here and therefore it will set. The stars primarily have names or Arabic names, and the question is why. And the answer is, simply put, that during the time of the great Arabic empires, there was a lot of science going on. This is pretty much the same time as the Middle Ages in Europe. And so those names for the stars continued. On the other hand, the constellations, though, are mostly Greek. Now, there are lots of these stars that we talked about, the 5,000 ones. There are more stars than that. There are millions and billions, as we talked about in the preceding lecture. But there are a variety of different ways that we can name these stars. So the brightest ones have names, but every several years a new catalog of stars is created. And as technology has improved, we see more and more stars. So what ends up happening is these stars get names depending upon the constellation that they're in, the actual, the name. So this is the second brightest star in Pegasus, and then another catalog would use just numbers and then the constellation name. And then we got even smarter yet, and then this is the catalog name, and this is the number of the star. So there are a variety of other star catalogs. This is from the Hipparchus satellite, for example. So here is a picture of Orion showing the Bayer number or Greek letter along with the Arabic name. So here we have Betelgeuse identified with Alpha. So this would be Alpha Orion. And then if I look down here at Rigel, Rigel is Beta Orion, and this is one of, I think, two different constellations where Alpha is not the brightest star and Beta is not the second brightest star. In this case, Beta is the brightest star, and the way I can tell that is this number is smaller than that number. So when we talk about brightness in terms of stars, we use a magnitude scale, and the magnitude scale is sort of like first place, second place, third place. So first place is better than second place, is better than third place. So in this particular case, a first place star is brighter than a fourth place star. We can see patterns as humans in anything, and some of these patterns are sort of ridiculous. Here, this is, we name these patterns in constellations, but this is the Big Dipper, as you know. The Big Dipper is really an asterism. It is not a constellation. And here is the constellation of Ursa Major, of which the Big Dipper is a portion of it. So here is the Big Dipper, and here is the rest of it. And there are more stars, this star, this star, this star, this star, this one. These are all part of Ursa Major. Constellation names are mostly Greek mythological features or names. They remind us of those things. They may or may not be characteristic of them. I mean, like this is Lyra, the harp, and it didn't look like a harp at all, although that's what it's supposed to look like. Now, constellations in the modern thinking is just a location in the celestial sphere, in the night sky. There are 88 of them, and here are a variety of them. And any one particular star is in a constellation, one of these 88 constellations. It's sort of looking at a map of Los Angeles and seeing all the different cities in LA. So you have a map of the Los Angeles basin, and you have all these city names. If you land in the basin someplace, you belong to a city. That's just it. And there are a certain number of cities in the LA basin, and that's that. If you live in the LA basin, you live in a particular city. So in the same reason, same idea, if a star is in the night sky, they're in a constellation. Then these constellations allow me to discuss with people on the phone you know, there is something really interesting going on in Cygnus. Here's a picture of Orion the Hunter, and you know, we can, you know, there are more stars in here than the ones that are picked out by this drawing, or the lines here. And in this particular case, it seems kind of silly that Orion is constructed this way rather than the other way, because Taurus the bull is over here and Sirius, you know, the major and minor dogs are over here. So it's kind of strange. And here's a time-lapse picture of Orion. Asterisms are parts of constellations, and we talked about that already, like the Big Dipper. It could also be other stars in different constellations, like the summer triangle or the winter triangle. They can be in different constellations. The ecliptic is another term that I'd like you to know about, and these pictures kind of interesting in the idea that when we talk about the sun being in a particular constellation, we're really talking about how the sun behaves relative to the fixed stars in the background. So here's the sun, here's the Earth, and when I look at the sun, it's in between Gemini, or it's actually in Taurus here. And so how do I know that? Well, when I look at if I look at the night sky directly overhead at midnight, then I would see Scorpius. And I would know that Scorpius is on the opposite side of Taurus. And so that's the way I know. I could also look at sunrise and sunset and pick out Pisces or Leo, depending upon how quickly it gets dark. The zodiac are those constellations through which the sun travels. It's also the path of the ecliptic. Currently, there are 13 constellations in the zodiac. One is not indicated here. It's called the Great Stank or Orpheus, something I can never pronounce it. Alrighty, let's continue. So, how do we tell where we're looking? Well, so we're going to be talking about position of stars in the night sky. And here is an example of a star map, and you can see that it's got horizontal and vertical lines, and that's basically how we start off with. But a little geometry first. We're going to use angles a lot. So 360 degrees in a circle, 1 degree has 60 arc minutes, and 1 arc minute contains 60 arc seconds. It's sort of like terrestrial navigation, the celestial navigation. Remember, after all, the celestial sphere is just a sphere that has this Earth nested inside of it. So if I move around on the Earth using latitude and longitude, then I should be able to do the same thing for the celestial sphere, and that's indeed what I do. So latitude is the number of degrees north or south of the equator. Longitude is the number of degrees east or west of a particular line. So here is the line that I'm talking about. This is called the prime meridian. It goes through Greenwich, England, which is close to London. And this is my latitude line, the equator. So the North Pole. With a system like this, I have kind of a strange problem with the North and South Pole, in the sense that the latitude is specified, but the longitude is not. The latitude is 90 degrees for the North Pole, and the longitude could be anything. Naturally, this gentleman is at a particular longitude if this is the North Pole. The same is true for the South Pole. Every other location, though, on the Earth requires you to have a latitude and longitude. So here's a couple of examples. Quito is in Ecuador is close to the equator, as is Nairobi. Okay, but they have very different longitudes. LA, this is something you ought to know, keep track of. We have a latitude of 34 degrees north and a longitude of 118 west. So, our first coordinate system that we're going to be talking about is a local coordinate system. It's characterized by azimuth and altitude. Altitude can be synonymous with elevation. So an azimuth is what you would get from using a compass. So north has an azimuth of 0 degrees, east would be 90, south would be 180, 270 would be west. And altitude is 0 degrees along the horizon, and altitude or elevation would be 90 degrees at the zenith, which is directly over my head. And nadir is directly below me. So here's a picture of what we would expect for the horizon. So the sun is either rising or setting, I can't tell here. But this line along here where the sun and where the sky and the land meet, that is the horizon. It's a local property. It changes depending upon where you are. The same is true with the zenith. This is a local property. It goes with you. Azimuth and elevation are local properties. So if you point to something in the night sky and you say it's there, you want to be a little bit more specific, and so you want to give somebody, azimuth and elevation. You'll be able to describe to somebody that's in your close proximity where you are looking. Now, how would you, so if you're in a star party, how would you do this? Well, one of the things you could do is say that, make the connection and use degrees. And as the lower left-hand corner says, use your body parts, because we're all human and we all share this. So, it's called the pinky rule. And if you spread your hands out, as indicated here, from your thumb to your index finger, that's about 20 degrees. A closed fist is 10 degrees, and each one of your pinkies is 1 degree. And your thumb is about 2 degrees. Okay, so in that way, you can describe where in the sky you're looking. Okay. Polaris is a star that's always very close to the latitude that you're at. For us right now in this day and age, and by the way, it changes over the centuries and millennia. You can see that with stellarium. And then we can, all right, so the second coordinate system is right ascension and declination. And the issue is with azimuth and elevation, is that if you describe to somebody on the telephone, say, here I am in Los Angeles, and you're talking to a friend in Perth, Australia, to look in the particular night sky, and you say, well, it's got an azimuth of 20 degrees and it's got an elevation of 60, then that location they're going to be looking at is going to be very different than the location that you're looking at, because after all, their zenith is quite different. They're looking into the southern sky and you're looking into the northern sky. Very different locations now. And so we need something that's more generic that we can all utilize, and that's what we use with right ascension and declination. Okay, so the idea here is, remember the clear sphere we had for the celestial sphere. We start off with the poles. The north celestial pole is directly above the North Pole on the Earth, and the South Pole has the south celestial pole as well. The celestial equator is directly above the Earth's equator, and your zenith then indicates a particular point here. Okay. Now the latitude and longitude, remember this is latitudes here, going from 0 up to 90 degrees, and so for the celestial sphere, we're going to have a latitude effective name coordinate system going from there up to here, and that is called declination. Okay, right ascension is the distance away from this spot here where the ecliptic is and along here. So that is where I draw my prime meridian, from here up to there and back around to the other side. And then so the star has a particular position in the night sky relative to that spot. So it's an angle east or west of the vernal equinox, and that is how I tell somebody in some other place, very far away from me, where to look in the night sky for this object. Okay, so that is it for this particular section. We'll go to seasons on the next one.